Okay, then we can start, I think. So it's my pleasure to present you Professor Shargorodsky Evgeny from King's College London and Technische Universität Dresden. And he will speak about quantitative results and continuity of the spectral factorization mapping. So please, Evgeny.
Okay, thank you. Many thanks to the organizers for inviting me. It's nice to be in Rostov, even virtually. Actually, I think I've been to Rostov just once, and it was about 30 years ago. I visited Rostov because Igor Borisovich Simonenko was my PhD examiner, opponent in Russian. And I do have very fond memories of Rostov, so thanks for inviting me. Now, this is a joint work with Lasha Premidze and Ilya Spitkovsky, both currently at New York University, Abu Dhabi, and they are the real experts in the field. I don't consider myself an expert in this field. I just joined my friends. Right, so I explain in about 10 minutes, I guess, what the spectral factorization is for us, what we mean by spectral factorization of matrix functions. But I will start with some background material on Hardy spaces. So just notation first, T is a unit circle, D is a unit disk, and we will need Hardy spaces. So you can introduce the Hardy space in two different ways. You can think of Hardy space as the space of functions defined on the unit circle. So you have functions in the usual LP. You look at the Fourier coefficients, and if the Fourier coefficients of your function G are 0 for all negative values of n, then you say that your function is in the Hardy space. So if this happens, you can extend your function analytically inside the disk. Now, this is because if you look at the Fourier series, you have GNs. The GNs are the coefficients, and then you have e to the power in theta, say, or in other words, z to the power n. You can extend this analytically inside the disk, z to the power n, and it is important that we don't have negative powers of z, so n's are non-negative. Otherwise, we would have had a singularity at 0. So we don't have that singularity. So the functions can be extended analytically inside the disk, and you can have a different definition of the Hardy space. Now you look at functions that are not just defined not just on the circle, they're defined in the unit disk, they are analytic there. And then to define the norm, you do the following. You look at your functions, at the circles of radius r. R is less than 1. So you go inside the disk, you take the concentric circles, circumferences of radius r, you take the usual LP norms, and then the supremum of those LP norms is your norm in the Hardy space over the unit disk. And there is you can identify these two spaces. So the space, the Hardy space on the unit circle and the Hardy space on the unit disk. So the functions on the unit circle are just the boundary values of analytic functions inside the disk. And this is one-to-one correspondence. It's isometric isomorphism. So this is not a difficult result, but it's not entirely trivial because there are situations different from LP where you don't have this equality. Say, for example, Alexey Karlovich and I, we have an example of a weighted LP space where the weighted Hardy space on the unit circle is strictly larger than the sort of boundary values of the corresponding Hardy space on the unit disk. Right, so, I'm terribly sorry. Let me just switch my email off so that it does not bother us. So let me create my email and yeah. Right, okay. Now, well, it is important for what we will be discussing. It is important for that to have, to remind you the notion of an outer function. So if you are familiar with the theory of Hardy spaces, and I assume that most people listening to me now are, you don't need to listen to me for the next, I don't know, 5 minutes maybe. But if you are not very comfortable with Hardy spaces, then I will try to not just throw the definition of an outer function at you, but try to motivate and explain what outer functions are. So suppose you take any function in the Hardy space, not identically zero, and it might have some zero in the unit circle. So let ANs be all the zeros of G in the unit circle. So we might not have any, we might have a finite number of zeros, or we might have uncountably many zeros. They cannot accumulate inside the disk because of the uniqueness theorem for analytic functions, but they can accumulate towards the unit circle. And then we consider this product, the Blaschke product. So I guess the most important part of it is the numerator here, an minus z, and you can see that as when z equals an, this factor is 0, so the Blaschke product has zeros at exactly the same points as G. And the rest of it, so this factor, for example, this is a sort of normalizing factor. It is needed to make sure that the product converges if we have infinitely many factors. And this power m is non-zero only if our function g has 0 at 0. Right, so this is a Blaschke product. And now this Blaschke product has the same zeros as g. So you can consider this ratio. And this is an analytic function. In the unit disk D. And it has no zeros. I think I'm getting some from somewhere. Maybe someone has microphone unmuted, maybe. Kind of. Okay, thank you. Right. So yeah. So if you look at this ratio, this is an analytic function. It has no zeros. So therefore, its logarithm is an analytic function in D. Now, and it is also important, and it's not a very difficult thing to prove, that the Blaschke product, its modulus equals 1 almost everywhere on the unit circle. So because it equals 1 almost everywhere on the unit circle, so this new function g naught with the zeros factored out and the original function g, their moduli are equal to each other at the unit circle almost everywhere. Now, so we have this analytic function, the logarithm of g naught. This is an analytic function, and we can write the Schwarz integral formula for this function. And the Schwarz integral formula expresses an analytic function in the unit disk by the boundary values of its real part. So the real part of the logarithm is the logarithm of the modulus. And because the modulus of g naught is the same as the modulus of g, we have this formula. Well, not quite, because although this is, the right-hand side is exactly what you have in Schwarz integral formula, there are some conditions that need to be satisfied for this formula to be true. And some sort of regularity conditions. For example, is if logarithm of g naught is continuous, say up to the boundary, then yes, this is true. But in general, this might not be true, and I will explain in a minute what happens here. But this is sort of quasi, semi-true. right? So, and then you can just write this. So G, our original function, equals the Blaschke product times G naught. This is just the definition of G naught, nothing clever here. And then you write G naught as the exponential function of its logarithm. Again, nothing clever here. And then we use this Schwarz integral formula that is not correct entirely. I mean, in this case, but so you just put the representation for the logarithms here. So you end up with this formula. As I said, it's not quite correct. There is a bit that is missing here, and this bit is this function S here. I will explain in a second what it is. Now, this representation is called the canonical factorization for a function in a Hardy space. Now, factorization here is different from the spectral factorization I will be discussing. So it's completely different. It's unfortunate that we have the same word here, but it means something completely different. So any function in the Hardy space can be represented as a Blaschke product. Now, this function G that we have already discussed, and this is the outer function, and this is the function that I'm mostly interested in. So this is outer function, and the bit that was missing there, it corresponds to a measure that is, I mean, this integral is similar to what we have in the outer function, but there the measure is just the integrable function times the Lebesgue measure. So this is an absolutely continuous measure with respect to the Lebesgue measure. And this is a singular measure with respect to the Lebesgue measure. So this one. Okay, so, and because this is a singular measure, it's easy to prove that this function is called singular inner function. So the singular inner function is the modulus of it. It is equal to 1 almost everywhere on the unit circle. And we know this about the Blaschke product. So what we have is this formula. So that the outer function, the factor in the representation, the outer factor in the representation, its modulus equals the modulus of the function almost everywhere on T. And actually, you can see that you can characterize this function G as an analytic function that has this property, the equality in red. But this is, there are many functions like that, because you can always multiply by singular inner function or by Blaschke product, and it doesn't change the modulus at the unit circle. But the outer function is the largest out of all those functions that satisfy this red equality here. So you can think of an outer function as a function that is responsible for the modulus of your function in a Hardy space. It kind of takes care of the modulus. And it doesn't have zeros in a sense. I mean, it doesn't have zeros inside, and it doesn't have very strong exponential zeros on the unit circle. So this is an outer function. And maybe a more intuitive way of defining it is the following. So the function is outer if and only if, when you take the products of this function G with all analytic polynomials. So those functions that you get are dense in the Hardy space HP. So then your function is, if and only if, your function is an outer function. It's sort of intuitively what it says is the following. Suppose you had a function that had zeros inside, say like Blaschke product. Then these guys would have zeros at the same point, and therefore they would not be dense in HP. So therefore you cannot have in your function a factor that is a Blaschke product. And for similar reasons, you cannot have a singular inner function there because it has, at some points of the unit circle, it will go to zero exponentially. So basically, let me perhaps go to the previous page and just to give you an example of this singular inner function. So suppose this mu, this d mu, is just a Dirac measure at one point. Then you will have this, I mean, single linear function, it will be just an exponential of this fraction for some t, right? So, and this function, you can see, will have exponentially strong zeros at the unit circle. So the outer functions don't have this. Okay, so this is what I wanted to say about outer functions. And well, I'm almost ready to go to the matrix case, but I guess this is my last page about the scalar case before I go to the matrix one. Right, so it is a well-known fact that if you have a function g in the Hardy space and this function is not identically zero, then its logarithm is integrable. Now, let me emphasize here, so this condition is not about how large g is, because logarithm is smaller than a power, I mean, for large values of the argument, right? So we already know that g to the power p is integrable. So when we say logarithm is integrable, it's not a restriction on how large the function is. It's a restriction on how small it is, because if you have a very, suppose the function is zero on a set of positive measure, say, so then the logarithm will be minus infinity on a set of positive measure, and obviously it won't be integrable. So this cannot happen. So this is a more sort of sophisticated version of the uniqueness theorem for analytic functions, if you like. So this says that a function in the Hardy space cannot have zeros that are too strong at the unit circle. So they cannot be sort of stronger than exponential. So again, so please remember, because this will, I will repeat this many times, I guess, unless I forget, that when we have this condition of integrability of a logarithm, this is not about how large the function is, this is about how strong the zeros are. Okay. Now suppose you have a function that is non-negative on the unit circle, and suppose you have these conditions that the logarithm is integrable. So both the function is integrable, so it's kind of restriction. This one is a restriction on how large the function is, and then the logarithm is integrable, so this is a restriction on how strong the zeros are. So suppose you have a function like that, then there's a unique representation of this function as the square of the modulus of an outer function. So there's a unique outer function. Well, if you normalize it at zero, so it's positive at zero, so up to a constant, there's a unique outer function that satisfies this condition. Now, well, because many people listening to me here have Rostov, Tbilisi, or Odessa background, where we were sort of brought up on factorization, the sort of Wiener-Hopf factorization, and I don't know, Simonenko's factorization. So this is obviously related to it. So if you just think of this square of the modulus as f plus times its complex conjugate, right? So we're representing the function as f plus times the complex conjugate. So this is a sort of plus function, the analytic inside. The complex conjugate of this function can be thought of as the boundary value of a function that is analytic outside. So this is a so-called minus factor, that the factor that is analytic outside, or the complex conjugate of the function that is analytic inside. So this is what we have in Wiener-Hopf or in sort of Simonenko factorization. Usually there you have one more factor that is responsible for the winding number. Now this factor is not present here because our function is non-negative. There is no winding factor here. There is no index here. I mean non-trivial index here. So from this point of view, this is a special case or a partial case of a sort of general Wiener-Hopf or Simonenko factorization. On the other hand, the emphasis here is this, that in, say, Simonenko factorization, we're factorizing a bounded function, f usually is a bounded function. And also it is a function that is separated from 0. So this is a function such that 1 over f is also bounded. So it's invertible in L infinity. So usually in the factorization, the way most of us know it's factorization that is used in tuplets operators, you have a function that is bounded and invertible in L infinity. So here we are only requiring that f is in L1, and instead of invertibility, we are requiring that the zeros are not too strong. So from this point of view, this is a more general problem. So it is related to the factorization that is used in tuplets operators, but it's slightly different. So in some respects, it's a special case. In some respects, it's much more general. Right, so I think I'm ready to go to the matrix case. All right, yeah. And so this is the formula. This is a formula for this, an explicit formula for the outer function that solves this problem. Okay, now the same in the matrix case. So let's Sn denote the class of matrix functions that are almost everywhere positive definite. So in the scalar case, it was just the function was almost everywhere positive. So we have that the function is integrable. And instead of saying that the log of f is in L1, we're talking, I mean, remember we were talking about how strong the zeros were. So here we will be talking about zeros, the zeros of the determinant. So the correct, sort of the appropriate generalization of the scalar one is that the log of the determinant is integrable, right? And then there is a theorem that says that any such matrix function, it emits a unique spectral factorization like we had in the scalar case. So we have this outer function times, in the scalar case, we had complex conjugate. Here we have Hermitian adjoint. Okay? So there's a unique function, outer function, that satisfies this equality. And this theorem was proved by Wiener in 1955, and I have to admit that I don't quite understand this proof. So, I mean, I have not spent days and days trying to understand it, but I kind of couldn't make sense of it. Now, Helson and Vladislav, they produced a proof that, well, I mean, even I could understand, although perhaps not entirely, because it was phrased in terms of stochastic, I mean, in probabilistic terms. And well, if you want a purely analytic proof of this fact, then there is a beautiful paper by Spitkowski and Mark Crane where they prove something that is more general than this. But for exactly this result, I think my favorite source is the book on the matrix factorization by Litvinchuk and Spitkowski. The proof there is so simple and clear. It's just a fantastic proof. For me, this is the place to read the proof. Right. Okay. Actually, I probably should have explained what an outer matrix function is. I mean, I explained this in the scalar case, but in the matrix case, it's more or less the same. I mean, there are, again, two ways of doing this. One is sort of maybe a cheaper one. So you, a matrix function is called an outer function. I mean, an outer function if its determinant, this is a scalar function, is an outer function. Now, the determinant will not be in H2, it will be in H2 over n, because the determinant involves products of n elements of the matrix, but this is not important. Or you can use a definition, the sort of alternative definition, similar to what we had in the scalar case. So a matrix function is an outer if and only if the set of these products, the function times all analytic polynomials, is dense in H2. Now, in this case, analytic polynomials will be with vector coefficients, but otherwise, this is exactly the same as what we had in the scalar case. So this is an outer function. Right, and so an important difference between the matrix case and the scalar case is that in the matrix case, we don't have an explicit formula. See, here we had, in the scalar case, we have a very explicit formula. Right? There is nothing like that in the matrix case, and therefore it is important to have a method of approximate factorization. And both my co-authors have a lot of results in this direction. I'm not going into that. I never worked on that, but I just would like to use this as a motivation for what we will be looking at. Now, when you are trying to do this approximately, and actually it makes sense even in the scalar case, because if you're trying to sort of approximate this, you are talking about a single integral in the exponential function. So it's not sort of just evaluating integral approximately might not be the best way of doing that. But we are interested in the case when we don't even have this formula. And then it's a very natural question, is the stability. So suppose I know that, well, I have, suppose I want to factorize f, right? And suppose I have an approximation of fn. Now, can I say that the factors will converge? Can I say that if I approximate the function, then factorize it, then whatever I get are actually approximation of the true factors, right? Now, one cannot expect that if you have just the convergence in L1, then you will have the convergence of the factors. You cannot expect that for the sort of very natural reason. Remember, in order for a function to have a spectral factorization, just belonging to L1 was not enough. We needed this logarithmic condition on the determinant. See, what you may have is a situation where, although Fn is close to F, F might have a decent logarithm of determinant, whereas this Fn might have a very bad logarithm of determinant that is about to fail to be integrable. So therefore, you do not expect these guys to be close to each other, because you might be violating, not quite, but about to violate the condition that you need for factorizability. So, but if on top of this, the convergence in L1, you have some control of the logarithm of the determinants, then you do indeed have the convergence of the factors. So this is good news, but you have this some sort of continuity. It's a natural one. So you have the quantities that are in the condition of the theorem, and if those quantities for two vector functions are close to each other, then the factors are close to each other. So this is what this result says, and it was first announced by Janasha, Lagvilova, and Ephraimidis in 1999, but they didn't publish proof until 2011, but a completely different and alternative proof was published in 2004 by Barclay. This was a PhD student of Jonathan Partington in Leeds. And this is the proof, the Barclay's proof, this is the one that we will be using, I mean that we have used in our paper. Okay, so, but the problem with this result is, although this is a qualitative result, it says that yes, if everything is fine, then you will be approximating the factors in the factorization. But it does not really help you if you are if you want to have rigorous results on approximation, because it doesn't tell you how small so this should be, or how close these integrals should be to each other, in order to have some sort of quantitative control. So if you're doing this for real, you want to know, you want to have some sort of guaranteed bounds on this in terms of, say, this quantity and maybe the difference between those integrals or something like that. Otherwise, it's almost meaningless. I mean, it doesn't tell you much. So, and here, so this is the question that we're trying to address. So can we have an estimate? So when you estimate the distance between these two factors, by some quantity that depends on the distance of the functions between the matrix function in L1 and between the logarithm, again, the distance between the logarithms of the determinant in L1. So these are the quantities that participate in the conditions of the theorem. So it's very natural to try to have some control of the distance of convergence, if you like, of those factors to true ones in terms of these two quantities. So the question is, can we have such an estimate? Is there any function of two variables, alpha and beta, such that it goes to zero somehow when both arguments go to zero? So this is the question. So can we have a quantitative result? Now again, let's go back to the scalar case. I'm just repeating what you have already seen. And so I think I had that bit early on in the talk. And then if you look at the boundary values of your function, this one, the outer function, then you can, it's a well-known fact that it can be represented like this. So it will be, the real part here is just the logarithm of your function. And the imaginary part, the argument, will be given by the harmonic conjugate, or this is the periodic Hilbert transform of your function. So it's a well-known formula. Now, my point here is that we have an explicit formula. Well, it's not a very simple formula, but so here you have the logarithm. So this is something not very scary. Well, we have this harmonic conjugate, the Hilbert transform. Again, we know a great deal about how harmonic, about the Hilbert transform. This is the main operator in harmonic analysis. We know a great deal about this. So you expect to be able to say something positive. I mean, you have an explicit formula. Now, surprisingly enough, there is nothing at that level of generality that I can actually say, because there's an example of functions. So you can have functions. I'm talking about scalar case. You have functions that are in L1, actually in the unit ball of L1. They are as close to each other in L1 norm as you like. And the logarithms are as close to each other as you like in L1 norm. So all the conditions that we have, they're satisfied. And yet, if you look at the factors, now the distance between them is almost 2. Now you see, remember that the square of the modulus of this function is just Fn. So this means that the H2 norm of this function is less than or equal to 1. The same for the other function. Its norm in H2 is the norm of Gn in L1, so it's less than or equal to 1. So we have two functions, Fn plus and Gn plus, that are in the unit ball in H2. And yet the distance between them is almost 2. They're almost like diametrically opposite to each other. They should be as close to, they should be very close to each other, because the difference between the data is very small, arbitrarily small. And yet these factors are almost diametrically opposite to each other. So it shows that you cannot possibly have any estimate whatsoever at this level of generality. And this is a very sort of discouraging result. Now, one might suspect that I'm cheating a little bit. One might suspect that the difficulty here is the following, that I sort of swept under the rug. So saying that, look, I have control of the size. It's not just that the functions are close to each other. I control their size. But in the conditions here, I don't control the size of the logs. Maybe log of Fn and log of Gn are huge. Well, yes, they happen to be close to each other, but they're huge, and this causes non-convergence. It's not quite true. You can just have some control of those norms, and then you perhaps lose just a little bit. The result will not be quite as striking, that the points are almost diametrically opposite to each other. But it's still, you will still have no convergence. You can say that there are functions that satisfy these conditions. Say you control logarithm, and then you still do not have convergence. That fn plus and gn plus will be the distance almost 2 from each other. So you cannot have an estimate. And while on the other hand, you want to have some sort of result to apply in when you try to approximate to do approximate factorization, right? So you still want to have some control, and therefore the natural question is that can we have some sort of estimate if we put additional restrictions on functions? Actually, what I would like to do is not put an additional restriction, but rather use an additional information. I mean, maybe it's a sort of philosophical difference, but nevertheless, I would like to make this distinction. So you see, the starting point here is that every function that is in L1 is not just integrable. It's just a little bit better than integrable. It might not belong to any LP with P greater than 1, but it will belong to a certain Orlich space. That will depend on F, but still, it belongs to some Orlich space. Now, again, some people might not be very comfortable with Orlich spaces. Let me just remind you, I will spend like maybe 5 minutes, maybe less on this, remind you what Orlich spaces are. So suppose we have some sort of underlying measure space, and we have psi that is a non-decreasing function, and we want to have a generalization of LP. So we want to have a Banach space of functions for which this integral is finite. So you put the modulus of f into your function psi, some non-decreasing function, and you want to have a space of functions like that. Now, if psi happens to be t to the power p, the p's power, then what we have is just LP. So you want to generalize this LP. Now, there are at least 2 issues with this. Now, the first issue is the following. So you see, if psi is very rapidly increasing, very rapidly increasing, say, for example, exponentially increasing, then the set of functions that satisfy this condition is not a linear space. I mean, for example, if you know that this integral is finite, you cannot say that it will be finite when you multiply your function by 2. Because in the exponential case, you're squaring your integrand, right? So therefore, you can't multiply functions, for example, so it's not a linear space if you're looking just at this condition, star here. And also, this is not a norm. You see, in this case, when psi equals t to the power p, this is not the norm. This is the p's power of the norm. So you need to have the norm, you need to have a p's power root of this integral. So, and it's not entirely clear what this root is for a general psi. Okay, so, and of course, this is very well-known stuff. So first of all, you need to be clear about what functions psi you allow. That usually in this business you allow continuous convex functions that decay at 0 faster than t and go to infinity at infinity faster than t again. And then you have a sort of a so-called complementary function that is defined here. This is a standard thing in convex analysis. If you sort of don't have, if you see this for the first time, there is no need to concentrate on this. What is important for us is that this will be the function that corresponds to the dual space. It's like the function for which you will have Hölder inequality. So, and therefore, these functions and functions, they come into pairs. So for LP, so t to the power p, the complementary function will be t to the power q, and 1 over p plus 1 over q is 1. Okay, and actually there are not that many explicit examples, and a very important example is this one, where b is this function, and this is important because the space corresponding to it is the space that is called log, so L log L. It's not just L1, it's slightly smaller space. That is, the function is integral when it's multiplied by its logarithm. So, and this is a very important space in harmonic analysis, because most operators in harmonic analysis are not bounded from L1 into L1, but they are bounded from L log L into L1, or from L1 into weak L1. So this is an important example. Right, and then when you have this sort of, you have a pair of mutually complementary n functions, then you can define the norm in, I mean, there are two main ways of doing that. One is sort of reminiscent of Hahn-Banach theorem, actually. So the norm is the supremum of these integrals, where g, and the integral of g, when you put this g inside the complementary function, is less than or equal to 1. And another one is you are looking at the integral, almost the same integral we started with, but now we are dividing this by some constant kappa. And the idea is that, well, suppose kappa is very large, so we're dividing by a large number. Remember, I had that issue, then when you multiply, say, by 2, you might lose integrability. Now here you start with dividing by, say, large kappa, so you expect this to be integrable, and so for large kappa, hopefully the integral is less than 1. Then you start reducing kappa, and the infimum of those kappas for which the integral is still less than or equal to 1 is another norm for f, and these two norms are actually equivalent. So this is from Krasnoselski and Rutitsky bookcase, if you like. So right, and the Orly space is the space for which these norms are finite. Okay, so now I think, yes, I need one more additional bit of information. It's not important. I mean, the estimates that I will show you, they do not have sharp constants. They have some constants. The point is they're explicit constants. They're not sharp, but they're explicit. Right, the first ingredient here is the constant k. As I already mentioned, operators in harmonic analysis, like the periodic Hilbert transform, are not bounded from L1 to L1, but they admit so-called weak type 1-1 estimate, and this is the estimate. This was first proved by Kolmogorov, and let k be the sharp constant here, and the sharp constant is known. And so this is the result by Davis, 1974. So this is a explicit formula for it. So K0 will be this product. As I said, it's really sort of, maybe I'm wasting your time because our constants are not sharp. Anyway, so here is the result. Okay, one more function. Right. So basically, this formula is quite difficult to digest. Now, think of this as a function, lambda, psi, that can be constructed by psi. So there is a definition, but it's kind of not terribly intuitively clear one. Okay, so never mind. So what is important for me is that for any psi, you can construct this function lambda psi, and it will go to 0 when the argument goes to 0. And in the example of LP spaces, you can do this explicitly. So if psi happens to be tau to the power q, I mean, never mind this factor here, I mean, it's just a constant, then this function is q's power root of the argument. So in some cases, you can do this explicitly. Now, and here is the result. Now, so we're trying to, so we start with this function, f. Now, as I said, any integrable function, we know that f is in L1, any integrable function belongs to a certain Orly space. So this psi obviously depends on f. Now suppose, and this is not an additional restriction, this is an additional bit of information. For every function f, such a psi exists, so this is not a restriction. But suppose somehow you know this psi. By this psi, you construct the complementary n function, psi, and then this ugly lambda capital function. So this can be done in principle. And then you stick into this function the L norm, L1 norm of the difference of logarithms. So now you have an estimate. Well, at this level of generality is not a very sort of good-looking estimate, but now if you do want to have an additional restriction, now this is an additional restriction. So suppose your function happens to be in LP. Then you have an explicit estimate. So now you have this power of this norm of the difference in L1. This is an explicit power here. So this is 1 over P prime, 1 over Q. So P minus 1 over P. So now this is an explicit estimate. And the best estimate you get if your function happens to be bounded. And then you have the power 1 here. And this you cannot expect better than this. So now this is a sort of the best possible estimate. Again, I'm not talking about the sharp constants, but as far as the powers are concerned, so you have the correct power here, just first, and the same for the difference of logarithms. Now, if you go back here and you can say, well, is this the correct power here? And turns out that yes, it is. This power is the best possible here. You see, ideally you want to have as large a power here as possible, because we're in a regime when, say, F and G are close, and you want to have F plus and G plus close, so the logarithms here are also close to each other, then the norm is small, so you want to have the right-hand side as small as possible, so you want to have the power as large as possible. And you cannot have any larger power, because if you take any gamma that is larger than that power, then you can construct a function f and some functions converging to it, such that, well, we have what we need to have, the convergence of functions and convergence of logarithms, and yet the difference between the factors cannot be estimated above by this higher power of the norm of the difference of logarithms. So the power is optimal. So this is what we have in the scalar case. And although my talk was mostly about matrix case, I kind of don't have much time to go into details, but I'll try, I'll do my best. So obviously, when you have a negative result, in the scalar case, you cannot, I mean, you have the same negative result for the scalar case. So how about the positive results? And for positive results, we need one extra quantity to control. And this is this quantity. So you take the logarithm of the determinant of a matrix and you subtract n times the logarithm of the norm, actually maximum between 0 and the log of the norm of it. Now look, we're talking about non-negative matrix functions here. Now the determinant is the product of the eigenvalues. You have logarithm of the product. So you have the sum of logarithm of eigenvalues. So basically what this says is the logarithm of the determinant is the trace of the logarithm. So, okay, so you have the sum of logarithms of eigenvalues of your matrix at each point. Now, the norm of this, I mean, the norm of that, again, is the largest eigenvalue. So here you have the sum of logarithms of all eigenvalues. So here you have logarithms of the largest eigenvalue taken n times. So therefore, this thing is a non-negative, sorry, non-positive thing. So we'll need this LF, and we will also need e to the power, the modulus of LF. So in other words, you have the maximum between 1 and the norm of the matrix function f to the power n divided by the determinant. Now again, so these are, so we will have conditions. Either we will control this quantity L, or we'll have an exponentially stronger control. Now, and again, I would like to emphasize this point. This is not a restriction on the size of the matrix function. This is again sort of a restriction in the scalar case at least. So this is a restriction on the strength of zeros. So in the scalar case, this is LF is just the logarithm of 1 over f, which is the positive part of it. The positive part of the logarithm 1 over f. It's called measures how small the denominator is. The same here, QF is the maximum between 1 and 1 over f. It's not about large values of f capital, it's about small values of capital. Now, in the matrix case, it controls sort of how different the eigenvalues are compared to each other. Or more precisely, they control how small the determinant is compared to the maximum between 1 and the nth power of the norm of f. So you see, the huge difficulty in the matrix case is that you may have, say, suppose you have a 2 by 2 matrix function. One eigenvalue might be very, very small, and the other one might be very, very large. And the determinant is of moderate size. So you see that you will have some sort of problem in this case. Now, here is an absolutely ugly and disgusting estimate, but don't worry, I'll try to talk you through this one. Now, first of all, I have copied the scalar result. It's in the sort of top line there. It's just to be able to compare what we have in the matrix case. Now, in the matrix case, let's just get sort of unimportant stuff out of our way. Everything that is in black is more or less the same that you have in the scalar case. So, for example, L1 norm of the difference we have for matrix function, while it's multiplied by 4. In the scalar case, it was multiplied by 2, but constants are not important to us that much. Now here you have a sort of norm of f in LP naught. This is similar to what we have in the scalar case. And then we have logarithm of norm of G minus logarithm of norm of f. And this is again similar to what we had the last factor in the scalar case. This is exactly the same. And then we have this term, logarithm of the ratio of two determinants is the difference of logarithms of the determinants. It's in the scalar case, again, this would be the same last factor there. So all of this is the same as in the scalar case. Now, you can see that, now let's look at the color, this stuff in color. So first of all, in the scalar case, we didn't have this restriction. We didn't need it. We didn't need to control how small the function was. In the matrix case, we need it. Well, and also, so look at this factor. So this is the norm of the difference in L1. It's not quite to the first power, it's 1 minus alpha, but alpha you can choose as small as you like, but then it will appear in a negative power in the other term. So, but this is not a problem here. I mean, you are almost hitting the correct exponent here. But the thing in red, this is a problem. See what happens here. So you have G minus F, L1 norm, which is small, logarithm is large, and then you have a negative power. So this is a small thing. But what you have is that if you want to have some sort of convergence, in the scalar case, we have first power here and some reasonable power here. Now that first power turns into logarithmic convergence. We have power 1, degree 1 convergence in the scalar case. And now we have just logarithmic rate of convergence. Logarithmic. So this is a dreadful result. I mean, it's an awful result. You have almost no convergence. You have logarithmic rate of convergence. Well, if you take slightly stronger assumptions, say if you say that the function was not just in LP, it was in L infinity, then the powers here, they improve accordingly to what we had there, so that this logarithm, L1 norm of the difference of logarithms appears in first degree. This is fine, but we still have this. And then you can think that, look, maybe our result is just very weak. I mean, you are dropping from the first degree of convergence to logarithmic rate of convergence. And so one might think that this is, we're just not clever enough. Well, this might be the case, But it turns out that the logarithmic rate of convergence is there for a reason. You might improve, it's possible, maybe, we don't know. Maybe it's possible to improve this power slightly, but you cannot improve it beyond minus P1, even for 2 by 2 matrices. So the best you can achieve, if anything, is that by improve your convergence rate by 1 logarithm, and that's it. You cannot improve it any further. So I'm about to wrap up. So in the case when you have an exponentially better control of the sort of size, comparative size of eigenvalues, instead of logarithmic term, you get some power convergence, power rate of convergence, but then again, it's not the first power of convergence that we had in the scalar case. It's some sort of power that depends on P1, and actually, well, again, you can improve it slightly if you have L infinity for a function. It's bounded, but again, you cannot improve this too much. Even for 2 by 2 matrices, you might be improve it slightly, but you can. The only thing you can hope for is to go from this fraction in red into this fraction in black that is not much larger. So it's not a huge improvement. So you can see that the rate of convergence will be genuinely slower. Now I will just skip, we have a general result like the one I started with in the scalar case for general only spaces, but it's even uglier than the one we have in LP. So let me end with a nice one. If you have function, matrix function that is bounded and that LF is bounded, then you have the rate of convergence that you like. I mean, then you have the first degree of convergence. I think I stop here. Thank you.
Thank you very much for a beautiful talk. So it was a real pleasure to follow you. Probably there are questions. So it was completely clear.
The question, small.
Please remember. Okay, yes, please.
My question is following. So the results is very interesting and I think very new. But my question about application, this result, and also so the problem of the factorization of the matrix function is very known and very interesting, has interesting application to partial differential equation. So the solution of partial differential equation, method of factorization of the function. But there is some application to this problem, to the problem of partial differential equation. This result about the factorization.
Well, I would not start from partial differential equations in this case. I think the applications are. Oh, sorry. So the applications are mostly sort of in prediction for stochastic process, prediction theory for stochastic process, control theory, filtering, and I mean all sorts of engineering, and also, believe it or not, neuroscience. Lasha showed me, I don't know, more than 5 papers. People, I mean, in neuroscience, where people are using this matrix factorization. Now, you cannot do it explicitly, you want to approximate. Now, and this is something that Lasha has spent a lot of time working on, and Ilya as well, but I think that sort of as far as applications and approximations are concerned, I mean, it's Lasha who knows a lot about this. Now, again, let me just repeat what I already said, that this is slightly different from what I was used to. when you have Wiener-Hopf factorization or factorization in tuplets of it, you usually have this problem with index, for example. And for matrix functions, indices are unstable. So for matrix functions, I mean, it is inherently very, very difficult to have any reasonable approximation. This is a very, very difficult problem. Now, in this case, we don't have this problem with index because we have positive definite matrix function, non-negative matrix functions. However, in many applications, it looks like, again, I'm very ignorant here, you need to talk to Lasha, but my impression is that in many applications, they have matrices that degenerate at some points of the unit circle. And therefore, the methods that were traditionally used in factorization, there are other methods. I mean, imagine you have even rational, think of a rational matrix function, rational. I mean, you go to Goldberg and Feldman, and there is an algorithm how to factorize a rational matrix function. However, it doesn't work in the case where your matrix function is allowed to have zeros. And it looks like in many applications, singular matrix functions, they do arise. And therefore, you will need to be able to factorize positive, say, definite matrix functions, but ones that are singular. And this is where you need sort of to have reasonable methods, and this is what Lasha is working on. But I would say that the results that I showed you, unless you have some control on this quantity LF, I mean, you have logarithmic rate of convergence. So actually, in practical terms, you don't have convergence.
Okay, thank you.
Thank you. Probably in the inverse transform method for solving nonlinear PDEs, one of the approaches is via the Hilbert problem and factorization of this sort. Okay, probably that was that Vladimir had in mind, yeah, when asking the question.
No.
Okay, the other questions, please. So the microphones are muted, please remember.
Нет вопросов больше.
Are there questions or comments? So it was too clear, you see.
Of course.
I agree.
Yeah. Really very nice talk. So thank you once more. Thank you very much.
Thank you.
Thank you. And I hope to see you in Rostov soon.